Hello, this is the video about entroppment. So this website, you probably have our DataEntroper. So you have open code or you have a compiled version using your compiler. If you want to make a build, change this one to EC. We have also tested on Ubuntu. There are some issues with some versions of Ubuntu about clipboard. We make some workaround for them, but this is just demo, so yeah, you can find the windows. So today we are about to speak about entroppment in context of loops, so encrypting, decrypting. And of course, this is not a cipher, but to speak with people, I need a terminology that is understandable. And when I start talking about projection and so on, it could be hard to understand because there is no ontology for that is commonly used, because this is completely orthogonal to cryptography. So we start our program, test loops. If you want to make a test, you take some, let's say, string, paste it, push testing, some number, loading K bundle, which is provided in the program, but you can generate in the program more of them. Some redundancy. For today we are skipping if, and you start test. After test, you can copy the direction of the file, and you can go there by going to the Explorer, Ctrl V, so paste, and you're gonna end up where the program is saving the files. Of course, I made the test previously, and I'm recording this like fifth time. So I'm just about to show it, the test, and explain what it consists of. We are mostly interested in our buffer, so you don't need to paste strings. You can intercept the buffer directly and push whatever you like. If you are about to create a reasonable utility from this. So I guess you're gonna be using some Solomon for buffers, because we expect loss of data. So level report, this one we are not changing. Okay, and we are closing the program after it is finished. Let's go to the file itself. This is this test loop file. So here what we have, where the test start, and then a lot of data. First we go to the end. During the process we have K interferences. This is very interesting because where we are pushing fakes, let's see, fakes, infuse false random blocks, we are checking if the key that would be used for decrypting by the end user is interfering with the random key we use for encrypt random data, so fake blocks. And we are checking how many nonce, not numbers, it's gonna have, how many numbers will gonna be in the range of the correct key, and how many numbers would be out of the range. Probably 0. Probably 0, 1, or 2. Probably 16, 15, or 14, because some of them could be nonce. And the thing is, there for encrypting a lot of blocks, like testing about 1,000 fakes, we found one of them. So we have 1, where the fake key and the real key use it. Those are just still in the testing process. Normally you will not give access for hardware security module to anything external, but this is testing function, so obviously I made a loop that is stealing the key to show something in the test. So the numbers that will be gathered by those two keys are different, but our checksum of nonce, correct numbers in range and numbers out of range are same, and I call it interference. So, however, those numbers are completely different, as you see. The issue is our end user, legal user, will find them legal if we skip those two checks. And because he found it legal, he will change his key in the process, and the two key bundles will decohere. This process is here, extract numbers, yeah. And if we have numbers, we rotate keyring. So those random numbers from real block are used to change our key bundle, and they change it very aggressively, not reversible. So if you're looking for this function, it is rotating keys, and you will found it in line 113. No, not 113. 122. So to get those numbers, we are using not key number 0 that was used for encryption, but some random key, because we randomize. This is not random, but let's call it some other key, which is currently on the position 1. So by attacking the open code, you don't know what this key is, and we get some random numbers in form of those. Those are very good numbers. They are not random, but let's call it that name. And they are used to change the key. So if this interfere with our real user key, so he will get this, let's call it a checksum. Same. He will use the fake block to change his key, and everything will collapse. So this is very important that we are checking this, and yeah, for 1000 blocks we have found one interference. 1000 fake blocks. It is 1080 or something like that. Okay, now let's go to the grand summary. So we have tested 3 loops. This is our average error. Maximal error is 1.4%. Average is under 1, average 1.1, and minimal error is under 1%. So Solomon will do this clearly and solve our buffer for such a loss. And this loss guarantee that function is not reversible. So even if using correct key, the information is lost. Some information, not many. If you're using wrong key, data are completely scrambled and you can expect error over 50%. Exactly 54 to 56% bits are wrong, and this is not symbolic encryption using bits, it is floating point. So if you change just 1 bit, you can be very near or completely off. Okay, this is timer, so how much time we spend encrypting and decrypting and so on. And how many blocks were sent totally, how many real blocks, fake blocks, real blocks received, fake blocks received. So how many of them and so on. If all those are same, we have a coherency between our key bundles. So after sending another message and another, our key bundle will change. However, we're gonna have consistent symmetric key bundles between sender and receiver. Of course, you can use it in loop to send and receive using same bundle, but you need to organize it, because if you send two messages with from Alice to Bob, and then Bob sent one message, he need to keep in history. Let's go to keys. This is the history key he used, and here is the current key he's using. So he need to check in history when the message was sent and what is his key for decrypting this message. So key bundle in this term. So it is far more useful to use one key bundle for sending and one for receiving for every pack. From those key I showed you, you don't need a lot of them. 3 are enough, but to make things funnier you can use 100 or 25 or whatever number. As far the key bundles are same for the symmetric for between both users. I'm very bad in explaining things. Okay, this is our sequence. Let's call it kind of oracle, anti-oracle. How many nuns? As you see here, we have on the position 0. Here we have at the position 8. Here we expect none in position 8, 2, 4. So they are coming sometime. Those are value in range, so most of the value are in range, and sometimes we see value out of range. It is very rare to get value out of range, but they came sometimes. And if you try to attack and you find the real key for real block, and you are doing analytical attack and you see value out of range or some not numbers, usually you would skip it. So it is not possible for any reasonable analytical attack that is shorter than enumerating all keys to find what is the real message. There will be a lot of minimums that will make a fake message. Here we have comparison of the bits. So how many bits were lost, how many blocks are received, and so on. And here we have decision. Block is fake, block is fake, block is real, block is fake. So this is using this comparison of arrays. So as we see here, block is fake because when using our legal key, we get those nuns and we expect something else. So block number 184 is out of legal, so I didn't save them. But as we see, this is wrong. Here we have a key rotation because block is real, so we are rotating our key using the previously mentioned function. So we decrypt the block that we already know. Block is real, block 181 is real. We are decrypting it again using the next key that is unknown, which is the wrong key for this block, but we want to extract same numbers as the sender have used for changing his key. So we are getting the numbers, we are changing our key bundle, and you never know what will be the next key. The sender knows because he's encoding this. And so we are doing all the time. As you see, negative numbers occur sometimes, and they do much funnier things. They are changing the case 2 times by this value. So there is a lot of funny things added in, just to make it a bit more complicated. But this is beyond any analytical attack that is shorter than enumeration. And so we have this function checking if the block is real or fake or so on. Let's go up. This is the sequence of the blocks that were real in the cipher, and what blocks were fake. So what we found, who is real, who is fake. As you see, there is a lot more fakes. And this is a raw cipher that were sent, shortened, because those are F64 numbers. And this is the raw bits clone. So our buffer, just here presented as an array of zeros and ones. And so we're gonna have for every test. So you see, this is probably encryption. Is it? Yes, this is encryption, and so on. So what key bundle we are using, and what was the numbers, and what key bundle we currently have. As you see, this is rotating all the time. So for every block we are using different key, and we are using key number 0. Let's go to 0. 0, key 0. Oh. Here we have key 0. As you see, every block is encoded with a different key. So with attacking this with 52 Mantissa key, let's have a fun. Like, this is enough to kill any computing power. But in 2026, nobody will tell that 52-bit number key is safe for cryptography. But this is not a cryptography, and that's the point. Here, 52-bit number without handshake and other overheads, it is good enough. So this is the whole procedure we are using here. Again, Oracle. And so we have a lot of information, how the whole process was performed. So this is our initial bit array we are encoding, and every time we were sending the same message, but every time cipher was different. Even if you use same key with same message, I mean open text, cipher depends on fakes, and they are, let's say, random in as computer can get random numbers. They are deterministic, but every time you encrypt something, cipher will be different for same open text. You can expect this. If you not set the function to be exact same as you expect. So in any normal circumstances, you can expect different cipher from same encrypted message. In case you turn the fakes to 0, the cipher will be exactly the same as every time you encode it. So the fakes change it. And you can put fakes here in the program. They are set to be number 3. Paste something. Here is the fake value. You can change it to whatever absurd number you want. It depends of your paranoid level. So for every block, 63 fake blocks, yeah, it doesn't do much, just the buffer will be gigantic. So the cipher will be gigantic. And another thing, which is important. Here we are encoding for every 64-bit number we are sending float. The real carry capacity is 30-bit. In the toy version, which is here, it was 32 bits, but then I found how I have to narrow the data to get them reasonable, and it ended up around 42 bits. So I use this space from 40 to 44 or 36, something like that, just to make different alphabets. So we don't know the encoding, if it is by 30 or 36 or 34 or something like that, just to make it more complicated. But this is purely deterministic. The issue is that you cannot find the key under enumerating all key, and even then there is no oracle that can tell you that you have found the right key. That's the whole issue about this. This is purely projective thing. So even if you are using the legal key, message is still a bit lost. How much loss? Here we have BER, so bit lost, and they are in this test on 1.4%. But you can expect max 2.1% losses in reasonable size message. So let's conclude the reading of the test function loop. Thank you.